Hi, our topic is comparative analysis of reinforcement learning for carbon-aware energy management systems. Energy management systems, also known as EMS, balances energy generation and consumption. Since the cost of energy can vary with time, EMS helps us to optimize strategies on battery charging schedule that overall reduces the bills. We want to propose this RL-based controller that can make a real-time and online decision utilizing the vast time series data. Also, as more and more renewable energy is incorporated, we want to maximize the use of these clean energy sources according to their inherent variability. In our model, we also include the price of carbon emission so as to emphasize the sustainability. In our system, we're revolving around four key entities. First of all, there's the demand side, representing anything from a building to an electrical vehicle. Traditionally, the grid has been our main source of supply, with prices fluctuating over time. But now, with the introduction of a PV generator, we've got some new moves to make. We can either buy power or sell any extra we've got, or we can put the surplus energy in our battery, which acts as the reservoir for both generators and it is the supplier of our load. We assume that any demand that cannot be met is fulfilled by the grid. When the grid price is low, we might decide to stock up for later, but when it's high, we may want to buy less. We apply the Markov decision process and define the set of states as load, PV generation, state of charge, meaning how much energy we have in the battery, and the price of the grid. And a set of the actions are the battery charge or discharge, energy from PV to the battery, and from PV to the load. When it's charging, ET is positive and vice versa. Note that the superscript here is the intended destination, where the energy goes, and this subscript T denotes at time T. The variable we have mentioned are all time variant. However, the only thing we can control is the SOC, which is the agent, leaving the rest of the environment. As such, the transition dynamics are on SOC, which has a certain capacity that composes these constraints. Our reward function is price of grid energy times the energy supplied by grid, plus the carbon tax times the emission amount in transmission. We utilize 4RL algorithms such as TRPO, PPO, recurrent PPO, and A2C. We choose these algorithms because they can train the multi-discrete action spaces. We built two types of EMS. Basic EMS only considers energy cost, while carbon-aware EMS considers energy and carbon cost. Thus, carbon-aware EMS always has a higher cost than basic EMS. When we compare the learning curves, the performances are similar for basic and carbon-aware EMS. For both types of EMS, TRPO and PPO exhibit commendable convergence with a notable degree of smoothness and stability in their learning processes. However, recurrent PPO fails to learn the optimal policy and also incurs a higher computational burden. A2C converges faster than others, but cannot reach to the optimal values. We also compare the control results of basic carbon-aware EMS and the baseline model. For the baseline model, optimization-based control algorithms cannot be considered as a baseline in power system area, since solving optimization problems at each time step is not a practical way for large-scale systems. Thus, we set the baseline model that only utilizes the PV generators. It is a deterministic model that the costs are directly computed by the difference between the load demand and PV generation. By comparing the energy cost of each controller, basic EMS with PPO and TRPO has lower energy costs and among other algorithms. It shows 40% enhancement in energy cost efficiency. When we compare the carbon and total cost, Carbon-aware EMS with PPO and TRPO has lower cost among other algorithms. To sum up, by considering the advantage of RL algorithms for online decision-making procedures, the proposed carbon-aware EMS can be applied to the real-time operation of building management to reduce both energy and carbon impact. Thank you for listening.